All right, well, hey, welcome to May. If you can believe it, we're already a third of the way done with this class, and this quarter is just flying by. But today's plan is actually, well, just so you know where we're going, we're gonna start playing with identities. We're gonna start looking at more identities. We're gonna develop more identities, and we're gonna use these identities to help us start simplifying expressions that involve the trig functions and to solve equations that involve them. And that's really the big goal for this class, is to use the identities to help us solve equations. I will tell you that a big goal going forward for calculus, saying this is pre-calculus, is using the identities to simplify, to change the form so that calculus ends up being easy. All right, so that's our kind of our big goal here in this next chapter, in chapter 9. And specifically today, I'm just going to start introducing you to some of the techniques that we use to simplify, to change the forms of trig identities or trig expressions. And yeah, so basically just start giving you some of the little tips for that. So that's my plan for today. But before we go there, because I know there's homework due tonight, are there any homework problems we'd like to look at? You can type them in the chat box. You can yell them out loud.
I had a question. I just need to look it up real quick.
Okay.
Sorry. It's 8.2. And then it was just, if we could go over one of the, I think you just had to write out the formula. Question 8. Could we
Question
go over
8?
that? Yeah.
Sure. All right, so let's go take a look at 8.2, number 8. All right, so I'll share my screen. Find the right, there it is. All right, and I'm going to guess this is 8.2 under the practice, not video assignment. Yeah, okay. All right, so this one says we want to write an equation for the function graphed above. So it's going to be one of the trig functions, seeing we're in trig function world. So of the 6, sine, cosine, tangent, cotangent, secant, cosecant, what does this one make you think? And I think there are actually 2 good answers to this.
Maybe
What trig
secant?
function? I'm sorry, go ahead, Nicholas.
Maybe secant.
Okay, so maybe secant. I definitely like that as one of our possibilities. What would be another good possibility?
I guess I get a shifted cosecant.
Yeah, so this is either going to be a secant or a cosecant. And the way that you can tell is that it's a bunch of alternating smiles and frowns, right? And as you're looking at them, we're going smile, then there's a frown, and then there's a smile, and then there's a frown, smile, frown, smile, frown. All right, so I know I want to pick either secant or cosecant. All right, now, which one I pick, completely arbitrary. It doesn't matter. I can use either one and I can make it work. But I am lazy. I am lazy. I want to do as little work as possible. And if you're anything like me, then pay attention to this. All right. To do as little work as possible, I want to avoid a shift if possible. And the only difference between secant and cosecant is a horizontal shift. So if I can avoid a horizontal shift, I'm going to do it. So I want to think about which secant or cosecant actually has a smile here whose bottom is at 0. All right, well, remember the trick is to think about the sine or cosine that connects these, right? The way that connects those. So this would be a graph whose peak is showing up at 0. So that would be cosine. So that makes me think I want to use secant. Okay, so if I use secant of x, and I'm just going to start typing some stuff in here, all right, just to keep track of where we are. But I'm going to use secant of x. That way I don't have to do a horizontal shift. All right, but this is not sufficient yet, right? That there is probably more. We have to think about all the other things that might be happening. Do we have a vertical shift? Do we have a vertical stretch or compress? Do we have a horizontal stretch or compress, right? But this way, if I use secant, I don't have to do horizontal shift. All right, so the next thing I'm going to look at is where is the midline of this? Where is the middle of this graph? Right, because we know for regular secant, it's at 0, but this is definitely not symmetric about 0 because we've got our peaks of our frowns at -2, and we've got our smiles up at 6, and those aren't symmetric. So the question is, what's halfway between -2 and +6? All right, Danielle just gave me, unless that's a math gang sign, which I'm totally down with, by the way. Right? But okay, so it's 2, right? 2 is the halfway point. It's really easy to find that. Take the difference in the two values, the maxes and mins there. So 6 minus -2 is 4. Or sorry, is 8. Divide that by 2 is 4. So we need to go 4 steps from the top or 4 steps from the bottom. Either way, that brings us to 2. All right, so that tells me I need to have a vertical shift of +2 because my center line is at 2 instead of at 0. Okay, so that's the next thing that I get. Oh, and by the way, what I'm talking through here with my process is the same process I use for cosecant. It's the same process I use for sine and cosine. Tangent is a little bit more difficult with the vertical shift stuff, but it would be the same thing I would do with tangent as well, tangent, cotangent. All right, so now my next question is going to be, what's the multiplier out front of secant? So now I need to think about how far do I go from those center line or from that center line to get to those smiles and frowns. Because on a regular graph of secant, you just go 1 up and 1 down. But now notice that I'm actually going to have to go up 4 and I'm going to have to go down 4 to reach those. So I'm going to put a 4 on here. So when we did this with sine and cosine, remember what it did was it changed the amplitude, changed how tall or short the wave was. Well, for secant and cosecant, that's just going to change how far apart the smiles and frowns are, since they lie on the tops and bottoms of the cosine or sine. Okay, so we're almost there. Now all we're left with is, what about a multiplier in here? So this is a horizontal stretch compress question. And in terms of trig, the easiest way to see that is to look at what's our period. How far do we have to go until we repeat? Okay, so look at these smiles and frowns. Let's look at the smiles. I think those are easier. So we have one of the smiles is here at 0. The next one shows up at 3. And then the one after that shows up at 6, and so on. So we have to go a distance of 3 to get our new piece, right? To get our repeat. So that's going to help us figure out what that multiplier is on x. but it's not gonna be 3. All right, so let me actually just share my whiteboard real fast because I want to write something down here. So when we did this before, for like the cosines and sine, remember we had a cosine of bx plus c plus d. This b was related to the period. It was 2 pi over b. Now I know we're dealing with secant and not cosine, but they end up having the same periods. So what we need is we need this period to equal 3. Right? That's how long it takes for our graph to repeat. So I just need to solve this for b. And that gives me 2 pi over 3. So it's always 2 pi over the period, by the way. You can just take this to get the b. It's going to be 2 pi over the period for sine, cosine, secant, and cosecant. What changes if it's tangent or cotangent? How do you think we can find b?
Isn't it only pi?
Yep, it is only pi. So it's pi over the period. And that's because the period of tangent and cotangent was pi. So we're just taking the original period, whatever it happens to be, either the 2 pi for sine, cosine, secant, cosecant, or pi for tangent, cotangent. Okay, well, let's go back and put that in over here. So what I need for my multiplier on secant is 2 pi divided by 3. All right, so I think we took care of everything. Let's submit the question. Hopefully we get the green check mark. Yes. All right, so that's the general process. That's my general thought process when I do these, Danielle, is just, I think about what each of those pieces do, but I got to start with which of the functions I think that it is. Had we instead gone with cosecant, we would have had to have a horizontal shift, which would have added a c. And like I said, I'm lazy. I don't want to do extra work. So if possible, I go with the function that doesn't require a shift. And sometimes that's impossible. Sometimes it doesn't matter which one you're dealing with. It will require a shift, but if you can avoid it, avoid it. All right, so is that better? Is that kind of what you were looking for? Yeah, all right, thumbs up, I like it. All right, so any other homework questions, or are we good to keep moving on? All right, well, I don't hear any, I don't see any, so I'm gonna go ahead and hop up to the whiteboard. I'll be right back with you. All right, so today I want to start showing you why we care about identities. We've run into them here and there. You've seen how we can use identities to find other values of the trig function and all that, but that still might make you go, yeah, so who cares, right? But really, why we care about identities is twofold. All right. One of the things that we use them for is to simplify. Because we can actually have some pretty big, ugly, nasty looking expressions that really simplify down nicely. And I'm going to show you some examples of that today. All right, is really the rationale behind this. Okay, So that's one of the things that we tend to use identities for a lot, is to just simplify things. And you're going to go through this in this class and probably not like it. Most people don't like dealing with identities. I love them. This was the kind of stuff that when I was in high school and I was bored in like history class or something, I would just make up trig identities and try to prove them. Yeah, that's me. So most people don't like it, but I'm going to tell you that this is the stuff you need to practice now, so that when you get to calculus, it's going to make calculus incredibly easy. I also know that hearing that from me may or may not mean anything. Talk to the people you know who have gone through calculus and ask them how useful trig is. They will back me up. They will tell you that, yeah, you definitely want to get your fundamentals down. Okay, so that's one of the things that we're going to use them for. The other thing that we're going to use them for is to help us solve equations. Now, we're not ready for that yet. That's going to be a little bit down the ways. But that's the other big place where we use trig identities, is it's going to take equations, turn them into forms that are easier for us to solve. All right. So this is why we care about identities, but we're going to practice primarily the first one. That's where we're going to need our practice, is working on simplifying them. So we already have a fair number of identities, right? Let me just remind you, like, the list of identities that we already know. All right. So here are the identities we know. So I'm just going to give the groups. So we've got the reciprocal identities. Those were the like secant is 1 over cosine kind of deals. That made it so that we only have to know the big three: sine, cosine, tangent. We also have the quotient identities. There were 2 of those. And those were the tangent equals sine over cosine, and cotangent equals cosine over sine. But again, what that did was made it so that we really only need to know sine and cosine. Some others that we have the even odd identities. So those are all the ones that have to deal with plugging in negatives. Just remember that all of the trig functions are odd, with the exception of cosine and secant. Okay, those are the only 2 that are even. But the even ones, cosine and secant, you plug in a negative, you can just ignore it. For the others, for sine, tangent, cotangent, and cosecant, you plug in a negative, you can bring that negative out front. Okay, so those were the even and odd identities. We also had the co-function identities. And those were the ones that said that sine and cosine were related. So basically the sine of theta was the same as cosine of pi over 2 minus theta. The sine of one of the angles in a right triangle is the cosine of the other, right? And the same thing holds for tangent, cotangent, secant, cosecant. So we have the co-function, and then the other group that we had were the Pythagorean. The main Pythagorean was the sine squared plus cosine squared equals 1. And then there were the 2 other forms, the secant squared equals tangent squared plus 1, and 1 plus cotangent squared equals cosecant squared. Okay, so we already have a fair number that we know, but this list is just going to get bigger. By the time we're done with this class, I don't mean today's, but I mean Math 104, you're going to add to this list sum and difference of angles, double angles, half angles, power reduction, sum to product, product to sum. Okay, so we're going to have a whole bunch of others that we're going to develop along the way that all have their uses at different times for different scenarios. Okay, but I want to kind of practice with these, the ones that we know, and show you what I mean by simplifying expressions. So let's just dive in with this example right here. So here's what we're going to do. We're just going to simplify the following. So here's what this expression looks like. It's sine of x times cotangent of x plus cosine of x over 2 cotangent of x. So does that look ugly enough to you? If not, I can make them uglier. But let's start with this. So we've got sine times cotangent plus cosine, all divided by 2 cotangent. Okay, now, in terms of dealing with these and simplifying, let me give you kind of a list of strategies that we can use. Okay. The first one, make another list of strategies. The first thing that's always useful, if you've got no other idea, if you're like, man, I don't even know where to start, turn everything into sine and cosine. Because all the other trig identity or trig functions, all the other 4, can be written in terms of sine and cosine. So this is a good place to start if you've got no other idea. All right, so basically we're going to make use of the first 2 here, reciprocal and quotient, and let's just start turning everything into sines and cosines. So the sine is going to stay sine, but let's change that cotangent. Cotangent is cosine over sine. Okay, the cosine is still a cosine. And then on the bottom, again, we'll change those cotangents into a cosine over sine. So that's what I mean by this first strategy of just turn everything into sine and cosine. All right, now we're going to be able to do some simplifying. Notice first here, I've got a sine divided by a sine, so those are going to cancel. So I've got cosine plus cosine, which is 2 cosine of x. On the bottom, I've got 2 cosine x over sine x. So now let's do a little bit more algebra. We'll go ahead and cancel those 2's. So cross those guys off. And then I'm dividing by a fraction. So we'll go ahead and flip that thing over. So this is the same as cosine times sine over cosine. So those cosines cancel. And this just equals sine of x. Okay, so yay, we went through the motions. We turned everything to sine and cosine because Bruce said we should. I want you just to stop and look at this for a second. Look at where it started, and look at where it ended. So we had this gnarly looking fraction that had all kinds of different trig functions in it. And yet we were able to simplify it down to just plain old sine of x. That should make you happy. That should actually get you be kind of excited. We can take horrible, ugly looking things and make them look nice and simple. Oh yeah. Lots of times with these trig functions, we're going to be able to pull tricks like this. So we can take horrible expressions, and yet you're just using the identities, the relationships we know about them, and simplifying them down. Like imagine you had an equation, that was this equals something, no thank you. But if it's just sine of x equals a number, oh yeah, that's easy, man. That's an inverse trig function. Boom, done. Okay, so this is why we care about them. This is why we use them, to do exactly this, to take horrible expressions and make them a little simple, or simpler. All right, so this is what I'm talking about when I say we want to simplify. Now, this one, though, was very open-ended, right? It was just simplify it. We didn't know what the goal was. We didn't know how far to take it, because every step we made it a little bit simpler, right? Eventually, we got to sine of x, and that was a real natural. Okay, stop it here. But sometimes we don't know that, right? Sometimes it's nice to have an idea of where we're heading. And this is the other thing that you're going to see when we simplify, are what we call establishing or confirming identities. Let me just explain what that means in a second here. So establish / confirm identities. Okay, so basically what this is going to mean is that we are going to prove that the given equation is an identity. Just remember, identity means it's always true. Okay? The way that we're going to do this is we are going to manipulate one side and we're going to make it look like the other. And when I say manipulate, really there are two classifications of what manipulate means. We're going to use other identities. So like the identities we've already learned. And we're going to use algebra. And I think it's the second one that makes people hate identities. Because now all of a sudden we're expecting you to do all the algebra stuff you did back in the day, but with trig functions. Right? Example would be like this dividing by a fraction. We had to invert and multiply it. Well, that's an algebra step, and now it's got the trig functions in it. Or we're going to have to factor. We're going to have to use common denominators, or, you know, we're going to have to multiply stuff out, so square things. Okay, we're going to have to use our algebra. But using algebra and identities, we're going to be able to take one side and make it look like the other. So let me show you what I mean. Let's actually do an example of one. I'm going to start it down here and then bring it up to the other side, I think. But let's just say we've got this identity. Tangent of theta plus cotangent of theta equals secant times cosecant. So this is an identity. This is absolutely true. You take your favorite angle, put it in here, you're going to get a true statement. All right, but we want to prove it. So what we're going to do is we're going to take one side only, and we're going to do stuff to it, either algebra or trig, to make it look like the other side. All right, well, let's still make use of the same strategy. Let's turn things into sine and cosine. But again, really important is we're going to manipulate one side, only one side. So what I'm going to do is I'm just going to pick a side. I'm going to pick the left-hand side just because. We can pick the right-hand side if we want. But I think if we start with the left-hand side, it'll be a little bit easier to show the other side. All right, so I'm just going to fiddle with this. So the first thing I'm going to do is I'm going to turn these into sines and cosines. So tangent is sine over cosine. Cotangent is cosine over sine. All right, so now we need to keep manipulating this. In terms of trig, there really isn't a good next step because these are already just sines and cosine, but there's a really good step algebraically. You guys see what we want to do here? What might be a good idea to do at this point algebraically?
I was gonna say cancel out one of them, but then they both kind of
Okay.
cancel.
Unfortunately, we can't just cancel out, but I totally see why you want to do that. In order to cancel it out, we'd have to have multiplication here. But we don't have multiplication, we're adding. So unfortunately, we can't do that. Well, we're adding fractions. Let's combine these. All right, let's actually add the fractions together. So this is one of the big algebra tricks. You're going to do a lot with these because so many of the forms have fractions. All the reciprocals are fractions. The quotient identities lead to fractions, but you're going to get lots of fractions. So I'm going to put this actually on a strategy. And I'm just going to put here, yeah, let me just put add or subtract fractions, add fractions. So if you have fractions, add them together. Okay, the aforementioned why people hate doing identities, right? Nobody likes adding fractions together. Well, at this point, I'm just going to tell you, suck it up, right? We're in advanced math classes. Things like adding fractions now, yeah, we just do them. We may not like it, but we do them because we know how to do it, right? So let's do that. We need a common denominator, which in this case would be sine times cosine. So the first one, I'm going to multiply both top and bottom by sine. And the second one, I'm going to multiply top and bottom by cosine. So put those together, and I get sine squared plus cosine squared over the common. Okay. So I'm curious, do you guys see what we could do next to simplify this? Because I'll tell you, for me personally, there's a piece of this that's just yelling at me.
Can we simplify the
Screaming
top
at
to
me.
just one?
Yeah, totally. I'm going to take that top and just turn it into 1. Remember our Pythagorean? Sine squared plus cosine squared. That equals 1. That's going to be one of those things I promise you, like before the end of May, you're going to immediately see that and go to just, nope, that's 1. You're not going to think about it. You're just going to do it. All right, so let's simplify that for a second. So this now gives us 1 over sine of theta, cosine of theta. So think about where we are. We started with tangent plus cotangent. And we've done a little bit of manipulation to it using algebra and trig. And we are now down to 1 over sine theta, cosine theta. Oh, we're getting close. We're getting close. Think of this as the map. We know we need to get to secant times cosecant. So the question is there a way I can make this secant times cosecant? And the answer to that is yes, and it's pretty easy. We can write this as 1 over sine times 1 over cosine. And now use the Pythagorean identities. 1 over sine is cosecant. 1 over cosine is secant. And I think that's good enough. We all know multiplication is commutative. You can write it in any order. But there you go. We just established this identity, or we confirmed this identity, or we proved this identity. It goes by lots of different names. But we just showed that this must be true. We showed it must be true just by using facts that we already knew, the other identities, and our rules of algebra. Now, when I talk about proving things, you probably go back to geometry, right? You think of those lovely 2-column proofs where you had to write down the lines and then your justification. Well, I mean, that's what we're doing. We're just not writing the justifications, right? When I started, here would have been line 1, tangent plus cotangent. Line 2, this plus this. On the other side, reasoning, the quotient identities of trig. Then we go from here to here. Why? Adding fractions. Then we go from here to here. Why? Pythagorean identity. Here to here, multiplication of fractions. Like we could set it up just like proofs from trig. We're not gonna. Because we are sophisticated enough now that we see the justification. We see what it is, but the justifications are going to be trig identities, rules of algebra. Okay, so when you see one of these where they say establish, confirm, prove an identity, this is what you want to do. You want to start with one side, do some work on it until it looks like the other side. But I want to stress, I didn't touch the other side of this equation. I didn't one time do anything with it. And we have to be really, really careful. You're going to see this equation and you're going to be tempted to do things like add something to both sides, multiply both sides by a number, take a square root of both sides, or all the other things you've ever done with equations. I'm just going to tell you right now, if you do that, you are wrong. It's not advised. No, it's wrong. Because what you're doing when you do that is you're assuming that it's an equation. You're assuming that the equation properties hold. So you're trying to prove it's an equation by assuming it's an equation. That doesn't work. All right, that'd be like me saying, oh, everybody in the world has blue eyes. Why? Because everybody in the world has blue eyes. No, that's nonsense. That's not proof. Right? You can't prove a statement using that statement. So we're not doing that here. We're going to always start with one side, whichever side you want, and we're going to manipulate it to look like the other side. Okay, so that's another big strategy, which is adding of fractions. And in fact, it shows up all the time. So let me show you another one where we would have used that strategy just from the start. So let's try this one. Let's go with 2 cotangent of x is equal to sine of x over secant of x plus 1 plus sine of x over secant of x minus 1. Okay, so we're going to go ahead and prove the identity. All right. Well, we have choices. We can either start with the left-hand side of the equation or the right-hand side. And I'm going to tell you my thought process. My recommendation is always go with the uglier side. Now, I know words like ugly are subjective, right? What I find ugly may not be what you find ugly. What I find beautiful may not be what you find beautiful. But I think we could probably all agree which side of this one is uglier. It's the right-hand side. Now, in trig identity stuff, when I talk about ugly, there are definitely things that are ugly. Fractions, ugly. Things inside of my trig functions, so like if we had a sine of 3x, ugly. Right? If by any stretch of the imagination I have square roots, oh, ugly. Right? Really, what ugly means to me here is there are things that I can do with that side that are pretty obvious. Because if we just come back to this one, if you look at the cotangent, there's really only one good option for us right now, and that's to turn that into cosine over sine. But I don't know that that's going to be super helpful. On the other side, there's all kinds of stuff we can do, specifically the adding fractions. So that's what I'm going to do. I'm going to go ahead and put these together by adding the fractions. So that means I need to get a common denominator. So I'm going to take sine of x and multiply it by secant minus 1. It's the other denominator. And then we'll add to that sine of x times secant plus 1. Those. And then that's going to be over the common denominator of secant of x plus 1 times secant of x minus 1. All right, so I just added fractions together. All right, well now let's just do some algebra simplification. Let's distribute, let's group like terms, let's do all that lovely stuff. So on top, I have sine times secant minus sine of x. So that's from those two pieces. And then I'm going to get plus sine times secant plus sine of x. And I'm going to go ahead and distribute out the bottom. It's a difference of squares. So we get secant squared minus 1. So some more algebra, right? Just distribution. On top, though, I want you to notice that the signs, I have a minus sine of x and a plus sine of x, so I'll cancel those. And then the other two pieces are identical. So I can write that as 2 sine of x secant of x. So that was actually pretty nice. All right, and then the bottom, we'll just go ahead and leave that as it is for a second. But this is where we are after we added those two fractions together. Okay, so cool. That was a pretty good first step, but now we need to figure out what do we do now. So here's where I'm going to go back and I'm going to look at what I want. At the end of the day, what I want is 2 cotangent of x. Well, I've got a 2. That's awesome. But it doesn't really look like I have cotangents. So what I'm going to want is to start introducing cotangents. And cotangents, I'll even take tangents, right? Because tangents are pretty easy to turn into cotangents. Well, this is where we're going to come back to our identities again. On the bottom, I don't know if anybody recognizes this, but we're going to be able to change this into tangent squared. And that's coming from the Pythagorean identity. We had tangent of squared plus 1, tangent squared plus 1 was equal to secant squared. So if you subtract the 1 over, We've got secant squared minus 1 equals tangent squared. So I'm going to do that. Because like I said, tangents are just as good as cotangents to me. Because I can always just, move them around, flip them over to get cotangents. And then the other thing I'm going to do is I'm going to change that secant back into a 1 over cosine. So let's look and see where we are once we do that. So we now have 2 sine of x times 1 over cosine of x over tangent squared. All right, well, look at this piece where we've got sine times 1 over cosine. That's sine over cosine, which is tangent. So notice what I was able to do using these other identities is I got everything now in terms of tangent. And that makes me happy. That's getting me close. Tangents can turn into cotangents. A lot easier than sines and secants. All right, well, I'm going to do one more algebra step before we actually finish the sucker off. The tangent on top is going to cancel with one of them on the bottom. So we're left with 2 over tangent. But from the reciprocal, we know 1 over tangent is equal to cotangent. So there you go. We just proved this identity. We just showed that one side equals the other. Okay, so lots of algebra and trig, and it was all intermixed, right? I mean, we started with an algebra step, which led to some more algebra steps, which then led to some trig steps, which led to more trig steps, which led to some algebra, which led to some trig. So it's going to be lots of all of this. Yeah. You're going to have to remember your various algebra techniques. You're going to have to be able to start integrating your trig techniques in there. Okay, but I want you just to realize that this is your chance to practice. And yeah, it's going to be hard the first times. Of course it is. You certainly shouldn't, think, oh, I can just sit down at a piano and start playing like I'm in a concert hall. This is no different. You can't just pick up a baseball bat and be like, I could face Clayton Kershaw and get a hit. No. It's the first time picking up the bat. Okay, same thing here. Don't go in with unrealistic expectations. Don't go in going, oh yeah, this is gonna be easy. I'm gonna do it just like Bruce was able to do it. No, this is your first go. Expect those hardships. Just don't give up. Okay, don't give up. All right, so there's another good strategy in general when we're trying to prove identities. Add fractions. Okay, another one. And I apologize because nobody likes this one. Factoring. Sometimes factoring is the key to being able to do one of these identities. And let me show you an example. So here's another one. We're going to prove the identity. And this one's going to look like cosine cubed x plus sine cubed x divided by sine plus cosine is equal to 1 minus sine times cosine. All right, so that's pretty ugly looking. And again, if we would go to the which side is uglier, well, I would definitely say the left-hand side. So let's see if we can manipulate the left-hand side and make it look like the right-hand side. All right, so looking at this, you may not really be sure where to even begin. But what we're going to do is we're going to actually factor the top, because the top of this thing is a sum of cubes. So let me just remind you that there is a formula for a sum of cubes, a cubed plus b cubed. It factors to a plus b times a squared minus ab plus b squared. And at some point along the way, you saw that, or at least you should have seen that somewhere along the way. All right, well, that's exactly what we have here, where a is cosine and b is sine. So if I make use of that, that's going to turn this thing into cosine plus sine times cosine squared minus cosine times sine plus sine squared. And the bottom will just leave us sine plus cosine. All right, so we just factored the bottom. Or sorry, factored the top. Okay, but now we can start simplifying a little bit. I've got a cosine plus sine and a cosine plus sine on the bottom, and those are factors. So those are going to cancel each other out. So we're left with just cosine squared minus cosine sine plus sine squared. So again, let's kind of pause. Let's take stock of where we are. So we started with this big ugly looking thing. And if nothing else, at least we don't have a fraction anymore, which is a good thing because our other side, there is no fraction. So we're definitely on the right track. Also, if you look at where we're going, notice that we needed a minus sine times cosine. And I've got that right here, minus cosine times sine. So things are definitely looking good. But I still have to get rid of this cosine squared and I have to get rid of this sine squared. So any ideas on how to get rid of those?
They just equal 1.
Yeah, this is that Pythagorean identity again. Cosine squared plus sine squared. Those equal 1. So when I add those together, I get 1 minus cosine times sine, which is exactly what the other side wanted. So I'm going to put a check mark next to it because we got there. Okay, so we just confirmed another identity. This ugly looking fraction is actually the same. It's just 1 minus sine times cosine.
It's not 2 minus sine times cosine.
Nope, it's just 1.
Just one.
because I've got one cosine squared and one sine squared. And those together equal 1.
Okay, together they equal 1. Okay.
All right, so that's another big technique for you, is factoring. Now, the sum of cubes, yeah, you'll run into that occasionally, difference of cubes. The one that you run into a lot is a difference of squares. So be sure you go back and look at the difference of squares factoring. You're probably pretty comfortable with that one. But just factoring in general, we're going to do a lot, especially when we get to the second big part of this whole idea of identities with the solving of equations. We're going to do a lot of factoring. Okay, so another good strategy is factoring. Now, the next strategy I want to show you, this is a Bruce name for it, by the way. So this is going to be strategy number 4. But I call this miracle step. You'll understand why I call it a miracle step in a second. But let me show you an example of one of these that requires this quote unquote miracle step strategy. So let's say we've got this guy. We're going to go to sine over 1 plus cosine. And that's going to equal 1 minus cosine over sine. So this is another identity we're trying to establish. And looking at it, you should probably go, okay, yeah, no big deal. Seems like all the other ones, same kind of deal. In terms of uglier side, I don't know that one side is uglier than the other. They're both about equivalent. They both have fractions. The fractions don't look that different from each other either. Okay, so you think about the other techniques. So the first one was turn everything into sine and cosines, if nothing else. Well, there's nothing to do here. They're already all sine and cosine. And you go, okay, well, what about some of the algebra? Add fractions together. Well, I don't have 2 fractions to add together, right? Each side is just 1 fraction, so there's no add fractions together. And then you might go, okay, well, what about factoring? You know, there's definitely no factoring. So you're probably at the point where you go, okay, well, geez, I don't really know what I'm going to do. All right, well, here's what we're going to do. Let's take the second side, the right side, just because it doesn't matter. And what I'm going to do is I'm going to multiply top and bottom of this thing by 1 plus cosine of theta. And I know I can do that because it's a fraction and I can build up fractions by multiplying top and bottom by the same thing. I'm going to multiply by 1 plus cosine of theta. Okay, so first, let's just run with it so you can see that it is going to work. So let's distribute on top. On the top over here, I'm going to get 1 minus cosine squared because it's a difference of squares. And on the bottom, I'm not going to multiply it out. I'm just going to leave it as sine times 1 plus cosine squared. All right, now the top of this thing is actually just equal to sine squared. And again, that comes from the Pythagorean, right? If we go back to the sine squared plus cosine squared equals 1. If I manipulate that, if I just subtract that cosine squared over, I get 1 minus cosine squared equals sine squared. So that's what I did, right? All right, but now I get to do an algebra step. I've got signs on top and a sign on the bottom. I can divide those out. And I'm left with sine over 1 plus cosine, which was exactly the other side. So it works, totally works. This is an identity. We proved it. We took one side, we made it look like the other. Okay, so miracle step. Why do I call it a miracle step? Well, because it's like, where'd that come from? It's a miracle. The math gods smiled upon us and sent us the key. Multiply top and bottom by 1 plus cosine. Right? So it feels like a miracle. It feels like it just sort of like divine inspiration gives us this. All right. But it's not a miracle. There's logic behind it. Can anybody see why I multiplied by 1 plus cosine on top and bottom? Like, what might even be the motivation?
Is it because that was our bottom on the other half of the equal
That's
sign?
exactly it. Yeah. Remember what we're trying to do. We're trying to manipulate the one side to look like the other. So here's basically the thought process. All right, I need to get sine over 1 plus cosine. So that means I need to have a 1 plus cosine in the bottom. So I'm going to put it in the bottom. By putting it in the bottom, I also have to put it in the top, but that was the motivation. Similarly, I could have multiplied top and bottom by sine, the same kind of idea. I need a sine on top. Well, I don't have any yet, so let me put one on top. And that totally would have worked out too. Let me show you. What if instead, by that same kind of argument, we went, well, let's take 1 minus cosine over sine, but let's multiply top and bottom by sine. All right, so now on top, we're going to have sine times 1 minus cosine. And on the bottom, we're going to have sine squared. All right, well, you can turn the sine squared into 1 minus cosine squared using the Pythagorean. And then the 1 minus cosine squared, we can factor that. It's a difference of squares. So that's going to factor as 1 plus cosine times 1 minus cosine. And then those factors cancel. And you can see that, yep, we ended up with the same thing on the other side. So either way, both of these show that what we're doing is we're introducing what we need from the other side. Right? Where I'm trying to go needs a 1 plus cosine on the bottom. All right, putting it in. Or where I'm going is I need a sine on top. Okay, put it in. So this is a very common thing that you'll see with identities, especially when you have one fraction equaling another. That kind of form leads itself to this miracle step. I just call it the miracle step because it's a little bit easier to say than writing out, introduce the missing pieces from a fraction on the other side. Miracle step. But there are all kinds of other miracle steps, by the way, that we run into in math. Sometimes they are that divine inspiration that someone just sort of also went, oh, check it out. If I do this, it works. And you go, man, I never would have thought about it. Well, that's why they get their names attached to theorems and we don't. Okay? But this is another big step that we use, or technique that we use when we're trying to show identities. Okay, so regardless of the identity, this is the process. All right, so I could do tons of these. I could do them all day long. And like I told you, I kind of like doing them. They're fun to me because they're puzzles. I'm a puzzler. I love being able to go from one side to the other. I'm also really competitive. So if I run into one where I'm starting to have trouble, I don't stop until I figure it out because I'm tenacious. And that's my personality. And I think that's why these things really work for me. But the only way you're going to get better at them is by doing them, is by practicing them yourself. So I think I'm going to stop because I've already shown you lots of examples. I've shown you lots of techniques, but now it's time for you to try it on your own. So we're actually going to end class a little bit early. You don't get used to this, right? I don't really want to dive into the next identity because its derivation is probably going to take a little bit longer than the time we have. So I don't want to go there. So I'm going to go ahead and end here for today. So just a few reminders and some things. First of all, there is homework due tonight. Don't forget to get in there and finish those off. We have scheduled a quiz on Wednesday. We're not going to do a quiz on Wednesday. You guys just took an exam. No quiz on Wednesday. Okay, so on Wednesday, we're going to meet in here at the regular time. I will send out a Canvas message to make sure everybody knows. But we'll be meeting in here Wednesday at 11 o'clock for regular class, no quiz. Okay. But what we're going to do is basically develop more identities. We're going to make a whole list that are called the sum and difference of angles identities. And then we're going to play around with them and start getting comfortable with them. And that's going to be kind of the process here for the next couple of weeks is we're going to develop new identities and then we're going to play around with those new identities, then develop new identities, play around with those, develop new identities, right? It's kind of the same process. Okay, so I think that's all I have to share with you all. Any other last questions before we stop recording? Nope. All right. Well, hey, then with that, you guys have an awesome couple days, and I will see you all on Wednesday. All right. Have an awesome.
Thanks, Bruce.
Thank you.
Very much.